Hi folks, we're going to continue on with lesson 4 here, and let's take up a few of these um, derivatives. All right, so here the function now we're dealing with is the constant function f at x equals 5. So if we try to determine the rate of change, or a function for the rate of change, where we're keeping this x value in my rate of change formula variable, ideally at the end we should be getting 0 because we know the slope of a horizontal line at any point should be 0. So let's see what happens. So again, I'm always going to start with the definition of the derivative, okay, which we used to think of as the definition of the rate of change, but by keeping this x value variable, like we talked about earlier, we're actually creating a function that outputs the uh, rate of change for the given x value. Okay, so let's go ahead, limit it as h approaches 0. Now, this is where our function is a constant function. It doesn't matter what the input is. Doesn't matter whether the input is x, or x plus h, or 7, or 23. The output of this function, regardless of the input, is always 5. So f at x plus h is just 5, and f at x is just 5. And I think you're probably seeing where this is going, because what we have is 5 minus 5 is 0 over h. And of course, remember, we're only interested in what's happening as h approaches 0. And for all the values near 0, 0 over h is just going to be 0. And there we go. So regardless of what the input of x is, the output is this constant value of 0, just as expected. Okay, so here we're going to start to see some, commonalities. So this one here, we should know what the answer should be. So let's take a look here. I've got the limit as h approaches 0 of f at x plus h minus f at x all over h. And so here, let me input x plus h into my function. So it's 2 times x plus h minus, let's input x into the function, 2x all over h. And here, what do we have? 2x plus 2h minus 2x all over h. And lo and behold, the two x's cancel out. And now I can reduce the h in the numerator with the h in the denominator. So I'm taking the limit as h approaches 0 of 2. That's the only thing that remains in all of this. And the limit of a constant is just a constant, because this number is not affected by h approaching 0. But I would say that this is exactly what we were expecting, because this is just a line with a slope of 2. All right. This is now where things are going to start getting a little more interesting, because y equals x squared does not have a constant rate of change. Obviously, if I start drawing the tangents, I see that they have different slopes throughout. In fact, I know it's going to be negative here and then positive on that side, and we expect it to be 0 right at 0. Okay. So this is sort of our first exciting one, really, because we don't know what the answer is going to be. Okay, so let's do this one here. So again, limit as h approaches 0 of f at x plus h minus f at x. Notice I write this every time because I want to make sure that I'm inputting exactly what I'm supposed to be doing. Okay, and then here, let's input x plus h into there. So x plus h squared minus x squared all over h. And here, I'm going to have to expand this. X squared plus 2hx plus h squared minus x squared. And I'm seeing that regardless of the choice of x, these terms always cancel out. Okay, so whether I have a specific value of x or I leave it variable, these two terms cancel out. And look what I'm left with As before, I've got a factor of h. So here, 2x plus h all over h, and we have what we hoped for, which was reducing those h's. And now let's take a look at what we're left with. So h is approaching 0. But what about this 2x? X is a variable. But what's important to realize is that in this limit, whatever this number is that x is representing, it's completely unaffected by h approaching 0. Okay? It essentially acts like a constant within the limit. This portion was getting closer and closer to 0, so it's starting to disappear. But this expression, regardless of what the value of x is, remains the same as h approaches 0. And lo and behold, there is the function that gives us the rate of change at any point on the function y equals x squared. So if I want to know what the rate of change is at x equals 1, I just have to input this into my function. 2 times 1 is 2. If I want to know the rate of change at -1, I just input -1 here. 2 times -1 is -2. And you realize that that actually makes sense, because at -1, the slope of the tangent should be negative, as opposed to at +1, where it should be positive. And where do we expect the slope of the tangent to be 0? Right at x equals 0, and that's exactly what we get. So even just this little bit of investigation, we see that this seems to be making perfect sense. And so now, when I want to determine the rate of change for any point, I do not have to go through this whole limit rigmarole. I just input the x value into my derivative function, and it is done. All right, so you're going to keep working on these other examples throughout this lesson, even if you have to finish for homework, and I'll make videos for you to be able to check your answers. Okay, that's it for now.